There are at least 100 billion stars in our galaxy, the Milky Way. There are about 2 trillion large and small galaxies in the visible universe, approximately 200 billion trillion stars. Just take a moment to appreciate this number. And that's considering only stars. But we already know for sure that stars have planets, and in most cases, more than one. And when somebody poses the endless question, are we alone in the universe? It's somehow strange to hear the unequivocal, yes, we are alone. Indeed, among the thousands of confirmed exoplanets, there are plenty of Earth-like planets. You don't really suppose that such an unimaginably gigantic number of planets in the observable space is inhabitable. Or maybe it is. In fact, not everyone could appreciate the importance and the profoundness of this natural science question. And today we'll get some answers to this question. Buckle up, you're in for a treat. Some of what you will hear and realize may stun or even frighten you. In this video, you'll learn why finding fossils of a very complex form or another planet would be the worst news ever to make headlines. Can we be part of a space reserve? Or maybe we are just a character in some supercomputer. Stay with us to find out. Some of the facts may really shock you. The Fermi Paradox and the Great Silence of the Universe. Subscribe to the channel and like this video. It all started with a famous small talk over dinner. Unfortunately, this conversation became known only through third parties. They say that one day in 1950, physicist Emil Konopinski, Edward Teller, Hubert York, and Enrico Fermi himself, an American physicist of Italian origin, one of the creators of the world's first nuclear reactor, met at the university for lunch. Konopinski recalled that they first discussed numerous eyewitness accounts of UFOs, which was a very popular topic in the 1950s. Gradually, the conversation turned to the question of whether material objects can move faster than the speed of light. And Fermi made everyone laugh with a rhetorical question, then where is everyone? But really, where is everyone? Why haven't extraterrestrial civilizations contacted us yet? With our television and radio programs, we've been sending signals into space for about 100 years. We've also deliberately sent into space naive but daring signals for extraterrestrial civilizations. What's more, we've contacted thousands of space enthusiasts on the internet to recognize signals received by the Arecibo Observatory in Puerto Rico. As a part of the legendary SETI program, still nothing, only silence. However, according to Hubert York, Fermi then performed more specific calculations, multiplying the probabilities of the existence of Earth-like planets, the emergence of life on them, the development of intelligent life forms, and so on. As a result, he concluded that aliens should have visited Earth a long time ago and more than once. York says that Fermi made several suggestions at the same time to explain why this didn't happen. According to him, either interstellar flights are impossible, or they are not worth the effort, or technological advanced civilizations don't live long. But Fermi didn't know about wormholes at the time. And if he knew, he would probably say that everyone already had a wormhole in their apartment with a pair of curious alien eyes intently watching us. Or some other sense organs they had. Perhaps the Big Brother has been watching us all along. And he's damn right. Just think about it. Scientists are already seriously considering the possibilities of wormholes. And we just need to advance our technology a bit more to learn how to create them. But then again, the question arises, where are they all? One way or another, according to Hubert York, Fermi's conclusions anticipated the no less famous Drake question, the subsequent long-term debate about alien civilizations, and the eternal question of, where are they after all? 10 years after Fermi's ideas, Dr. Frank Donald Drake, professor of astronomy and astrophysics at the University of California in Santa Cruz, decided to comprehensively tackle this question. He came up with his famous equation designed to determine the number of extraterrestrial civilizations in the galaxy humanity has the chance to contact. This probability was obtained by multiplying the star formation rate, the proportion of stars with planets, the probability of the emergence of intellectual life on the planets, and so on. In total, there were 7 parameters. Of course, we are far from knowing most of these parameters, but Drake didn't formulate the equation to solve it, but merely to keep the dialogue alive. And he really managed to do it. Over the past 70 years, there have been many hypotheses and theories supporting the Fermi paradox and its reflection in the form of the Drake equation. So hello, where is everyone? Why can't we hear anyone, and why isn't anyone hearing us? One of the most debatable theories is that of the Great Filter outlined by Robin D. Henson of the Future of Humanity Institute at Oxford University. This is a kind of hypothetical barrier that can be set for humanity either in the past or in the future. The hypothesis concludes that the easier human evolution has been so far, the worse destiny we might have in the future. Doesn't sound obvious? Do you remember this joke? I intend to live forever. So far, so good. Well, it seems that we can easily apply it to all humanity, not just individual human life. Not so funny anymore, is it? When trying to understand why we don't see evidence of aliens, Henson questioned the high estimated probability of the existence of technologically advanced extraterrestrial civilizations. Some unknown factors can reduce the likelihood of an emergence and development of life forms to the point where traces of their activity can be registered by others. In part, it is precisely for this reason that the average lifetime of a civilization may turn out to be too short for it to intersect with another one within the same historical epoch and reachable region of space. This can be compared to the ripples in the water created by the thrown stones. If you only occasionally throw pebbles in the water, the ripples will get easily lost in the entirety of the pond. The analogy is obvious considering the scale of space and civilizations. While one civilization is still learning to use fire and the wheel, the other has already died in a nuclear war, or for any other reason. In the vast space of billions of parsecs and over billions of years, the chances for civilizations to miss each other are much higher than for ripples on the water in some pond. Isn't that true? Just think about history and how many times humanity has already been on the brink of destruction. But why say has been? We don't have to look very far. Do you remember the year 2020? The pandemic has reminded us that our entire civilization may only be a short glimpse in the history of the Earth. But let's go back to the scientific approach. Henson estimated the evolutionary stages needed for the emergence of an interstellar civilization. 1. The formation of a star system with planets suitable for life. 2. The emergence of replicable molecules such as RNA on one of the planets. 3. The rise of simple single-celled life forms, prokaryotes. 4. The development of complex single-celled life forms, eukaryotes. 5. The emergence of sexual reproduction. 6. The evolution of multicellular organisms. 7. Developing intelligence capable of using tools. 8. A civilization becoming advanced enough to colonize space. We've reached this level. 9. The spread of civilization through space colonization. According to the Great Filter hypotheses, at least one of these stages is extremely unlikely. If steps 1 to 8 are highly probable, then a lot of civilizations in the universe would have evolved to the current level of humanity. However, none of them seem to have made it to step 9. Otherwise, the Milky Way would already be full of colonies. So, step 9 might be improbable, and anything can prevent us from taking this step. A nuclear war, an epidemic, an asteroid, depletion of resources, underestimating some social processes, or anything else. Some very unexpected and discouraging implications may follow from these slightly confusing considerations. But let's indulge in some science fiction and imagine that we did find traces of life on these nearest planets. First, this would suggest that life can independently emerge on different planets, and it's an extremely common phenomenon. If we found the simplest life forms in Martian soil or under the ice of Jupiter's moon, Europa, this would mean that the Great Filter should be set somewhere after this period of evolution. This would have been slightly unsettling, but we could still hope that the Great Filter is in our past and that we have already passed it. If we were to discover a more advanced life form, such as some kind of multicellular organism, that would remove many more potential Great Filter periods from the universal timeline of any life form, and the chance that the Great Filter is in our future and not the past would increase significantly. But if we discovered the fossils of some very complex life form, for example a vertebrate-like creature, then this discovery would be both sensational and equally tragic. In this case, we would consider that the Great Filter is still ahead of us. Such a discovery would be a devastating blow. As Nick Bostrom said, that would be the worst news to ever make the headlines. Why? After all, such a find can suggest that life is indeed very widespread. But that's good. It's good, isn't it? But judging by the Great Silence, not a single civilization in billions of years has been able to break through the Great Filter. Do we have a reason to believe that we'll be the first? Once again, imagine that we started finding traces of extraterrestrial life everywhere. Yippee! But there is one but. We only find traces, and there's no evidence of living, let alone advanced civilizations. How does it feel to receive indisputable evidence of the existence of complex life forms in the universe and at the same time realize that we are never destined to contact them? Moreover, as a civilization, we are the most likely doomed because of the inevitable Great Filter whose nature we don't even understand yet. Now, don't you feel relieved when you realize that it's nothing more than a hypothesis? But it's our human nature that makes us see the future with great optimism and ingenuity. And it was human ingenuity that helped many scientists and intellectuals to come up with the alternative theories on what caused the Great Silence. However bizarre, many of these theories became widely discussed. Let's consider some exotic hypotheses. In order to understand them, we will need to temporarily disable our common sense. And there is nothing unscientific about that. After all, by and large, common sense is only the sum of the preconceptions of its time. Several centuries ago, Giordano Bruno wasn't driven by common sense. By the standards of that time, his executioners were the most sensible ones. This is the least extravagant of the exotic hypotheses, but this theory can instill the feeling of worry and dismay. Chinese science fiction writer Liu Cixin proposed the concept of a dark forest to explain the Fermi paradox. In short, it poses that the evolution of life in the universe applies continuous competition and survival of the fittest among advanced civilizations. Therefore, any significantly developed civilization carefully hides the evidence of its existence to avoid being attacked by competitors. The young civilizations that give this evidence away are like inexperienced travelers walking through a dark forest. He might think that there's no one around, but if he makes enough noise, sooner or later he will run into a predator. And alas, the traveler is dead before he knows it. We can clearly see how it aligns with Stephen Hawking's idea. Back in the day, he voiced some concerns about sending signals into space for hypothetical distant civilizations. Hawking argued that such actions are too naive and reckless, and if someone finds us thanks to such efforts, it may end badly for us. The history of South American civilizations clearly proves this point. But what if more advanced civilizations have long discovered us, but turned out to be far less aggressive than Hawking imagined? The next idea might sound totally crazy. This is the Serengeti National Park in Tanzania, the oldest national reserve in Africa. It's one of the most famous and largest national parks in the world. It is considered to be one of the most complete ecosystems on the planet. Its area is almost 15,000 square kilometers. It is home to 3 million large animals and almost 500 species of birds. The Serengeti is also famous for the annual migrations of hundreds of thousands of wildebeest, gazelles, and zebras. During the migration, animals cover around 3,000 kilometers. Although the Serengeti attracts tens of thousands of tourists every year, most of the local higher animals have never seen people. Not to mention those who established this national park and set restrictions for visitors. Ironically, it's quite fitting to consider them the creators of this isolated world. These animals don't know that they live in a large nature reserve. They are not aware of any boundaries, rules, and the creators themselves. For them, human civilization doesn't exist, and if they were smart enough, they too would wonder, where is everyone? As for the lower animals, the trope of a national park is redundant. To an ant or a butterfly, humans don't seem like a large and threatening species, but an incomprehensible phenomenon of nature, like rain, wind, sunlight, winter, or summer. What if somebody considers our world nothing more than a nature reserve? And by our world we mean not just Earth, but the whole universe. And we simply can't recognize those unknown powerful creators with our senses or comprehend them with our minds. Sounds too incredible, but that's not all. There are even more bizarre hypotheses. Here we are balancing on the edge of science, but we can't help but mention this hypothesis at least for one reason. Its author, Nick Bostrom, a Swedish philosopher and professor at Oxford University, known for his work on the anthropic principle. His article, Proof of Simulation, is considered to be the main work in this field. It was published in 2003 in the Philosophical Quarterly. Bostrom's main idea is that if we don't think that we are currently living in a computer simulation, we are not entitled to believe that we will have descendants who will run lots of such simulations of their forebears. In short, the main idea is as follows. Over the course of its development, technological civilizations create more advanced computer simulations. If we go a step further, we see that individual simulations become so complex that their inhabitants begin to create their own simulations, and so on. With some reservations, let's give credit to this theory, especially given the fact that our civilization actually does this and succeeds in creating more and more complex and realistic simulations. Computer games become shockingly lifelike. And if we assume that we're in one of these simulations, then the great silence of the space is just the rules of the game, the initial conditions, period. There are many exotic hypotheses like these explaining the great silence. And we haven't even mentioned here the most ridiculous ones. Surprisingly, all of them may turn out to be much more likely than the answer that is literally in front of our eyes. The most obvious one. The one that follows directly from the Great Silence. It's so unnervingly straightforward that we don't even want to say it out loud. What if we are really alone? And this answer sums up one of the most convincing theories that explain the Great Silence and the Fermi Paradox. But at the same time, it's the scariest and most frightening one, because it takes away our last hope. If you've been following this topic for some time, You're probably well familiar with an ironically ambiguous statement that the Earth is just another rocky planet in a regular planetary system near an inconspicuous star on the outskirts of one of the countless trillions of galaxies. Ironically, this idea wasn't proposed by hype-seeking tabloid journalists. It was along the lines of what Carl Sagan and Frank Drake said. Just like many other scientists, they believed that, given our planet's unremarkableness, the universe could well be teeming with life. This point of view even has a distinctive name: the mediocrity principle. And yet again we find ourselves wondering, where is everyone? Actually, everything is much more complicated than it seems. Thanks to some researchers, the principle of mediocrity found its way into the scientific pop discourse and didn't raise any questions until a few years after. You see, there wasn't much discussion on this subject, although there should have been more. But the discoveries of recent years still forced us to question the mediocrity principle after all. But if this principle is a bit frustrating, its alternative is much worse. It instills a sense of total loneliness, existential despair, and hopelessness. We may be the result of such a fortunate coincidence that it could be simply described as one in the whole universe. This idea has developed into a fairly consistent rare earth hypothesis. Peter D. Ward and Donald Brownlee's work, Rare Earth: Why Complex Life is Uncommon in the Universe, dives deeply into this issue. In the book, they make a compelling argument for why the emergence of complex life is an unimaginably rare or even unique phenomenon requiring exceptional astrophysical and geological coincidences. According to this hypothesis, a planetary system capable of supporting complex life should structurally resemble the solar system, and the slightest variation may ruin everything. Many people believe the so-called Goldilocks zone or habitable zone is virtually the only condition life needs to emerge. The Goldilocks zone is a region around the star where the conditions on the planet's surface orbiting the star will ensure the existence of liquid water. In our case, the uniqueness also lies in the fact that the Earth's orbit is quite round, and we never find ourselves either too far from or too close to the Sun during the year. And that's just the beginning. As we go deeper into the question, we'll find more and more conditions. Not everyone knows, but not only stellar systems have a Goldilocks zone. The Earth is lucky enough to be in such an optimal zone in our galaxy. That might not be the most obvious idea, so let's go into detail. It takes about 235 million years for our system to orbit the center of the Milky Way. That means since the oceans appeared, our planet, together with the Sun, has covered all the distance 17 times. It has done it 15 times since the appearance of the first actual traces of life, and 7 times since the rise of the first multicellular organisms. By the way, this hasn't been an easy fight. You could only loosely consider this distance complete emptiness in intergalactic space. A lot of unpleasant surprises may await our tiny solar system on its way through the galaxy. They can be fatal for the whole system, not to mention our planet. What's more, a dead zone constitutes the most part of every galaxy, the Milky Way included. This zone can't support complex life or give rise to any life at all. Why is that? The closer to the center of the galaxy, the stronger the destructive effort of X-ray and powerful gamma radiation emitted by the neutron stars and black holes with their jets. As you approach the galaxy's center, you see more and more of these monsters. And the closer you are to the center, the closer the supernovae flashes. And these are weapons of mass destruction, capable of destroying entire worlds from many light years away. In addition, proximity to the center makes gravitational disasters more likely. Even if a planetary system had optimal parameters, it would take one close flyby of a star, or worse, a black hole, to mess up the whole thing. At this point, we can already see that basic mathematics doesn't work. Statements like, There are hundreds of billions of stars in the galaxy and even more planets, which means the galaxy should be full of life, are fundamentally wrong. The thing is that most stars lie close to the galaxy center, which is packed with heavy action. Even if life emerges here, it won't last long. At the same time, being too far from the center of the galaxy is also bad. The farther from the center, the lower the star's metallicity, which is one of the key factors for the formation of Earth-like planets. Recent research suggests that the length of the galactic habitable zone is from 7 to 9 kiloparsecs. This is approximately 22.8 to 29.3 million light-years away from the center of the galaxy. Surprisingly, on average, no more than 10% of stars fall into this zone in the Milky Way galaxy, and that's taken into account the most optimistic estimates. However, time is the most critical factor. For billions of years, the planetary system should have suitable conditions for the origin and, most importantly, the maintenance of life. Therefore, the planetary system should preferably have an ideal orbit around the galaxy's center so as not to fall out of the habitable zone even for a short period. And lo and behold, the solar system lies exactly in the habitable zone of the whole galaxy, and its orbit is almost perfectly circular. But wait, there's more to it. Our entire galaxy is a pretty rare phenomenon. 10,000,000,000,000. 10 billion years. That is about how long the Milky Way hasn't collided with other galaxies. Let us remind you that the age of the entire universe is just over 13 billion years. This is part of the reason why our galaxy is a fairly quiet place, a safe haven if you will. On average, there are only 7% of such galaxies in the universe. And now let's remind ourselves that our galaxy is currently moving pretty fast towards its closest neighbor, the Andromeda Galaxy, and they will almost certainly collide. Perhaps this will be the great filter for our civilization? However, this won't happen for at least 4 billion years, but still. Although if humanity proves to be so inept that it can't venture into deep space in 4 billion years, then it's doomed anyway, for many reasons. Let's go to our next point. When gazing at those brilliant dots scattered across the night sky, we sometimes think that any of them might look something like our sun, except for different sizes and luminosity. But that's far from the truth. According to various estimates, about half of all stars in our galaxy constitute at least binary star systems. Take, for example, the North Star. The fact is, there are as many as 3 stars there, locked in a space dance with unpredictable trajectories. In sci-fi films, we have often seen a colorful landscape with the sunset or sunrise of 2 or 3 suns on a faraway planet in a faraway galaxy. However, there are a bunch of reasons why planets in such systems would most certainly not be a cradle of life. First and foremost, it's highly unlikely that these planets would have a stable orbit for billions of years, not to mention the issue of the habitable zone becomes much more complicated. But there's no need to go that far. Despite its seemingly mediocrity, the Sun has extremely rare characteristics. Our star is surprisingly stable and has a luminosity variation of just 0.1%. And even though many stars have been discovered that belong to the same class as the Sun, not a single one is known to have a similar mass, luminosity, age, temperature, and metallicity. And each of these factors plays a crucial role in the big equation and determines whether or not life is possible. There are a lot of issues like this, and we could discuss them for a long time. They include the strange structure of our solar system, the uncharacteristic location of gas giants, the fortunate presence of the moon which stabilizes the Earth's axis, and much more. But even if you take all these low probabilities combined, none of them come close to the barrier that really shifts our ideas on what's possible and what's not. We're talking about the origin of life and evolution. as we know it. Even if we make things easier and accept the panspermia hypothesis, which suggests that life came to Earth on a comet, the paradoxes of further evolution are unexplainable. Life on the planet survived two great glaciations that took place 2.2 billion and 635 million years ago. And who would have thought that these two seemingly cataclysmic events facilitated the evolution of life? The first stimulated the development of photosynthetic microorganisms, which greatly reduced the concentration of greenhouse gases and triggered the accumulation of oxygen. And following the second glaciation, the legendary Cambrian explosion occurred that gave rise to almost all existing evolutionary branches. As a result, the first brain appeared. Let's make a small digression for the sake of a complete picture. Such a dramatic and complicated history with several glaciations and mass extinctions contributed to the evolution of life forms and their complexity. If we found a hypothetical paradise planet with ideal conditions, most likely it wouldn't host life, or it would be too simplistic. There are no complex tasks to solve that require a lot of effort. There is no need to complicate things and evolve in paradise-like conditions. If things around you were super easy, why would you evolve into something more advanced than yeast? Therefore, no matter how cruel it may sound, contrasting conditions are absolutely needed for evolution. Favorable factors aren't enough. They should be balanced with unfavorable ones. Winter, summer, day, night, predator-prey, life, death. However unpleasant this may sound, it is an academic fact, and evolution itself proves this conclusion. This being said, the unfavorable factors shouldn't be too extreme, because life is still a rather fragile thing. How many factors should align in this kaleidoscope of probabilities to create a chain of events leading from a lifeless planet to a technologically advanced civilization capable of conquering space? Please keep in mind that we are making an assumption about panspermia, that life on Earth arrived already ready-made. But if we want to be completely honest with ourselves, we'd have to leave this assumption behind. After all, life had to emerge somewhere, somehow. Suppose there was a place in the universe where all of the above unlikely favorable factors came together. All habitable zones, the perfect combination of the star's parameters. A rocky planet, the presence of a large satellite, water and atmosphere, and so on and so forth. A completely identical twin of the Earth somewhere in deep space. So, what next? Nothing. The very first brick that modern science considers life is the replicator. That is a complex molecule capable of self-replication. It is only with the emergence of the first replicator that evolution mechanisms start to operate. But the first replicator itself must have come about by chance. And the problem is that even the simplest replicator is still too complex for it to appear entirely by chance. Scientists have run countless sophisticated computer simulations on this topic, and the results have given us more questions than answers. A recognized international expert in evolutionary and computational biology, Russian-American scientist Eugene Koonin, calculated the probability of the spontaneous appearance of the first replicator. He argues the number is 1 to 10 to the power of 1018. That is 10 with 1018 zeros. Just so you know, the number of atoms in the universe is 10 to the 80th power. This is 0. Compared to 10 to the power of 1018. It is essentially impossible to comprehend this ratio. Even such a prominent scientist as Eugene Koonin had to take up the multiverse hypothesis to somehow explain this incomprehensible number. At the same time, putting science first, Koonin reminds us that such a conclusion is too convenient, and that in order to stay within the framework of scientific discourse, we must lower the bar of assumptions and ruthlessly cut off the unnecessary stuff with a proverbial Occam's razor. Unfortunately, the dreamers won't like his conclusion. The emergence of life requires exceptionally unlikely events. Therefore, we are alone in our universe. Not only are we intelligent beings, but more broadly, the only living beings at all. Driven by cold calculations, this ruthless statement might not be the last piece of bad news for dreamers today. There is another barrier that seems just as insurmountable: the emergence of intelligence. It is a highly specific, complex, and insanely interesting topic. Although the rare Earth hypothesis has its fair amount of criticism, the counter-arguments mostly concern some very specific details. No matter how cruel the hypothesis may seem, it's still difficult to counter it with a more or less meaningful and well-argued alternative. But the facts are even more ruthless. Humanity has seen thousands of UFO cases, sent people to the moon and robots to Mars, has been listening to space with radio telescopes for many years, discovered thousands of exoplanets, and even launched spacecraft that left the solar system. And here we come back to our starting point. With our television and radio programs, we've been sending signals into space for about 100 years. We've also deliberately sent into space naive but daring signals for extraterrestrial civilizations. We've connected thousands of space enthusiasts on the internet to recognize signals received by the Arecibo Observatory in Puerto Rico as part of the legendary SETI program. Still nothing. Only silence. Even when the Arecibo radio telescope tragically collapsed, none of them seemed to be impressed. Nobody arrived. No one. But no matter how hopeless this great silence seems, it is by no means a verdict. Carl Sagan himself has been repeatedly saying his signature phrase: absence of evidence does not mean evidence of absence. At least because if the panspermia hypothesis is true, then life could well have gotten not only on our planet. This radically changes everything and turns the discourse on its head, and all these low probabilities don't seem significant after all. Finally, this never-ending search for extraterrestrial life and, moreover, intelligent civilizations has one major flaw. We really have no idea what variables and what variable sequence make up the great formula of life. And we don't even know for sure what intelligence is and what forms it can take. Then why do we think that only terrestrial-type intelligence is possible? Indeed, all this time we were looking for ourselves. But in fact, we're not even sure that life can only be carbon-based. Everyone who is at least a little interested in the topic has heard about hypothetical silicon-based life forms. But that's not all. For example, when exposed to very high pressure, around 460 gigapascals, nitrogen and hydrogen compounds become even more chemically diverse than hydrocarbons. It's therefore plausible that their derivatives are more diverse and numerous than all existing organic compounds. And here we are, only one step away from an alternative nitric hydrogen-based life. You can find suitable conditions for such biochemistry in the depths of the giant planets that contain huge amounts of nitrogen and hydrogen under extremely high pressure. But this is a completely different story and another set of probabilities. But we are still looking for ourselves, and do it deliberately. This way, we at least have some idea of what to look for, because it's impossible to look specifically for something you don't have the slightest idea of. Stanisław Lem spoke at length on this topic. Let us thus be honest with ourselves. We are not looking for any civilizations, but predominantly for anthropomorphic ones. We introduce the law and order of a scientific experiment into nature, and then on the basis of such phenomena, we aim to see beings that are similar to us. Yet we're not seeing any such phenomena. Is it because they are non-existent? There is something deeply saddening in the silence of the stars that awaits us in response to this question. A silence so absolute that it seems eternal. The great silence of the universe, supported by the rare Earth hypotheses, can really instill sadness or even fear. Fear of being fundamentally alone in the universe. But should we be afraid of loneliness or something else?